Great. Thanks a lot. The last talk of this session is by David Powell. It's online to confidence set conversions, applications to sparse stochastic bandits.
All right, so this is a joint work with Yasin and Csaba, and I'm going to talk about construction of confidence sets and application to bandits. So here is roughly the outline. So first, I'm going to spend some time explaining how to build confidence sets for very basic linear model. And then I will apply it to linear bandit problem with side information. And then we will specifically focus in both these problems on sparse weight vectors theta. So that's basically the problem that we started with. And so here are the details. So the linear model that we consider is simply we have a vector x, feature vector x, and unknown parameter theta star, and we observe a covariate yt plus some noise. So the noise is zero mean and it's sub-Gaussian. So essentially what we observe are pairs xy. So it's standard regression problem, and what we want to do, we want to estimate theta star given these observations and build a confidence set for it. Now just one more comment. We allow the situation where xt can actually depend on the previous observations. So it's not IID sampled. X's can be chosen arbitrarily, even depending on the past data. And so, okay, what is a confidence set, first of all? So confidence set, it's a subset of RD that can depend on the data, obviously, and then confidence parameter delta, such that with high probability, the true parameter theta star lies in that set. By the way, there is a bug on that slide that should be 1 minus delta. So think of delta as some small number, something like 5%. So this is what statisticians do all the time, pretty much, when they construct confidence intervals. Now we are going to do the same thing in just higher dimension. Okay. So what are the previous constructions? So basically what people do is the following thing. They stick these x's into a matrix, they stick the y's into a vector, and then simply they solve a system of linear equations, and they obtain a least square solution. And then around that least square solution, they build an ellipsoid, and essentially the shape of the ellipsoid is determined by the covariance matrix of the data. Now, so basically that's our confidence set. And the sort of what people prove is bounds on the radius of this ellipsoid. And the radius can depend on many things. In particular, it depends on the dimension, on how much data you have, on the confidence parameter, how much noise there is, on the regularization parameter, and so forth. And it can depend also on the data itself. So here is a particular example. So many people worked on this. So there is, for example, a paper by Danny et al., then Rusmivici and Tong and Tsitsiklis, they derived some bounds, and we worked on this also. We had a paper at last year's NIPS where we basically derive a shape of the ellipsoid like that. So here the assumption is basically that if you assume that there is an L2 bound on theta star, and you assume that your xt's are bounded as well, then this is basically the radius. It depends on the noise, so the bigger the noise, the bigger the radius, and so forth. All right. Now, so what are we trying to do here is basically derive confidence sets for the situations where theta star is sparse. Now, we know that there are algorithms that are good at estimating theta star if it is sparse, but only they do point estimation, so they just spit out one number. But the question is, can you give me actually a confidence set for them? And the question is the ellipsoid going to be smaller because of that? And we actually indeed show that yes, it's going to be smaller. All right. And so basically our construction is uses a reduction to online prediction problems. So what are online? Okay, so what we assume here is that we have a black box that you could feed into it pairs xy and then your current prediction xt, and it will spit out its estimate of yt, which we call y hat t. So think of it as an online prediction algorithm. I show it x1 and I ask it to predict y1. Then it does some update on its internal parameters. Then I show it x2. It spits out y2. I show it x3 and so forth. Now what we assume here is that such algorithm has low regret. So what does it mean, low regret? Low regret means that it has low squared error compared to the prediction where it would be just predicting using theta star. Of course, the black box doesn't know theta star, but it's learning it as it's receiving more and more data. So the hope is that there are algorithms which have small regret if theta star is sparse. And in fact, such algorithms do exist. All right. And so we just, in a way, misuse them for construction of these confidence sets. So basically what we do, in a nutshell, is this. We run the online prediction algorithm on our xy pairs, and it will produce some estimates y hat. And then what we do, we essentially calculate the least square solution where we replace the y's with y hats and place an ellipsoid around it. So our confidence set is essentially an ellipsoid around such least square solution. Now the radius of the ellipsoid depends on the regret bound that we have for that algorithm, which is kind of neat. So you can observe that smaller the regret, the smaller the confidence ellipsoid is. All right. So for example, here are some results about these online prediction algorithms. So so-called Wolf-Azuri-Warmuth forecaster is essentially, you can think of it as regularized least squares on the past data, has regret d log n. And then recently there was published a paper by Gerchinovitz which designed an algorithm basically that works well for sparse thetas. And the regret depends only logarithmically on the dimension, and it's linear in the sparsity. Surprisingly, we are not aware of such bound for things like lasso. So lasso has much worse regret bounds. In fact, they're polynomial in the number of rounds. It's something like square root of the number of rounds, which is rather unfortunate. As a side note, so for example, if you just want to derive the usual confidence set for least squares, you can essentially take this theorem about online least squares, use our conversion, and you will get an ellipsoid that's essentially roughly comparable to the best ellipsoid that you can get by other methods. All right, and then, so this is how you construct these confidence sets. And now, what do we do with them? So, the applications that we have in mind are linear bandits. So, basically, the setup is as follows, that we play the following online learning game. So we receive a set of actions that we can choose from, and then we choose an action from this set, and then we receive a reward that's linear in that action. We just don't know the parameter theta star, so our reward is linear. And our goal is essentially to be as good as if we knew theta star. So if you know theta star, you obviously choose your action such that it maximizes the dot product with theta star. So that's what the first sum shows. And your regret is basically just the difference of these two rewards. For example, you can note that the classical multi-arm bandit problem, where you have just D arms, and you are trying to find the best one, can be encoded in such a setup where the decision set is simply the set of unit vectors, standard unit vectors. All right. So one approach to this linear bandit problem is that you maintain a confidence set for theta star. So you never precisely know where theta star is because of noise. So you need to keep around the confidence set, and then what you do is you are trying to be optimistic. So you jointly optimize the reward that you can get from an action from your decision set and a theta from your confidence set. So this is basically the joint optimization that you do in every step. For example, note that, again, the classical UCB algorithm, where are you maintaining the upper confidence intervals for the arms, is just a special case of this. So that's the optimistic principle of reinforcement learning. All right, and then basically what we get, okay, so you can prove a very general upper bound for this optimistic algorithm that essentially depends on the radius of the ellipsoid and sort of the analysis of how it shrinks. And you get an upper bound that depends polynomially on the regret of the prediction algorithm and the dimension and the number of rounds. And so basically what we do is that if we plug in the Gerchinovitz algorithm into our framework, we are able to reduce the regret of the bandit algorithm by a square D factor and replace that square D factor by square root of the sparsity of theta. So I guess that's it.
Thank you very much. Any questions?
I lost everybody.
Okay, so in the setting you had, so in the linear setting, I can understand the choice of an ellipsoid confidence set. Is there clear once you go into the sparse linear setting that
it's not clear that it should
be a
no
confidence set that you're...
So the reason why we did this is essentially that then you can analyze how the ellipsoid shrinks, and the analysis was known for the other algorithms, basically that for the dense case. So that's the reason why we stick with ellipsoids. One can of course imagine that you would be using something else, and probably it is the right thing to do something else, but we don't know what.
Okay. Thank you very much. Let's thank the speaker.